Okay, so now I would like you to estimate the basic model that we are looking at, the L wage. We can go to the statistics up there to the right, statistics, and then longitudinal panel data. It's here, and then a linear model, and then linear model and regression, linear regression with panel data. So what I would like you to do is to estimate a model that is using the dependent variable L wage and then the independent variables, the ones that you were using previously, so I'm sure that you have them already. You should have them in the do file, because in the do file all this is saved. So if you have everything, this can be a possibility. And so what I would like you to do is, we can skip this one, because this is not necessary, but we are going to do is first estimate using between. Why between? Between is a very simple estimation technique that uses only the variation between individuals. It is based on the average. So let's look at the outcome. The outcome is similar to previous ones. We are not going to look at all the details, but remember what is typically happening here is that some of the variables are not significant because there is little variation, and there's only variation across individuals and not within individuals. Okay, so this is typical. So let's look at the within estimation. This is another technique. If you want, you can you don't have to go all the way. You just go to and recycle, and you put FE instead of B. You change so, and that would be the within estimation. That is covariance estimator, and we see that there are some variables that do not vary across time, and that is why they are omitted. They cannot be estimated, their coefficient. It doesn't mean that they are irrelevant. It means that you don't have information in your sample to be able to estimate those effects from the data that you have using this technique, the within estimator. Now, if you want to combine the two previous estimators into just one and have more efficient estimation, you can use the random effects model estimated by generalized least squares. So generalized least squares is going to be our next estimation. You can put RE here. You can put RE or nothing. Maybe you can drop everything, and then you get, by default, you get random effects. So this would be the random effects. So we already saw all these. We don't have to explain everything again, but see that now we can estimate the effect of some of the variables that have been omitted previously. Because we are considering now an estimator that uses the variation between and within individuals. So the next thing that we did not do the last time was the Hausmann test. So let's remember that the Hausmann test is a test for to decide if there is correlation between errors, individual errors, which are the individual alphas, and the regressors, X's. correlation. If there is correlation, bad, that means that we cannot use GLS. If there is no correlation, good, that means we can use GLS. So now let's see how you can do the Hausmann test. I told you last time that in previous versions it was very easy because you only had to say Hausmann, it would do it. But now it is a little more complicated because the test itself is very general. You can do tests in many different situations. It does not have to be a choice between fixed effects and random effects. It does not have to be a choice between the covariance estimator and the generalized distributor. It can be more general, and that is why it is a little bit more complicated. Remember that you have all these commands. You have them in the documentation that I gave you in the page. So you have all these commands in the page. You don't have to remember anything because everything is there. If you don't remember, you just go to the help, but you have it. You have it there. The help is in English, so you can always look at the help.
Excuse me.
Yeah.
For pool estimation, what command we should to write?
Which one?
Pool.
For pool, you don't use any. You use reg, R-E-G. So if you want to do pool, let's do pool for a second. It's the same. XT reg, anyone. So you take out the XT.
So it is a simple
Regression.
correction.
Yeah. And then you take out all these up to the comma. And then it. And this is the more simple. The more simple. And sometimes you may want to do this, but it's not very useful most of the time. Eh?
It's not a panel.
Yeah, that is assuming that it is not a panel. So let's go now to the Hausmann test. Hausmann test is very easy. You first have to estimate using the fixed effects. So you can estimate using OLS. How do you estimate using OLS? Like this. You do the estimation using the within estimator or OLS. And so you hit return. And then the next thing you want to do is you want to write estimates store fix. You can give any name, but fix so that you remember. Estimates store. ES. So I have the commands here, but you also have them in the documentation. And Angel is going to write it again here. Estimates store fix. So you hit return, and it doesn't tell you anything, but just if it doesn't tell you anything, it's good. If it gives you a red sign, it's bad. So the next thing is you estimate again using the random effects estimator, in this case generalized least squares. So let's look at the generalized least squares estimator. So well, so now you have estimated the equation twice. Once using OLS, the other one is using GLS. You stored the estimates of fixed. So typically what you can do here is you write Hausmann. You want to use this command here. Hausmann fix, and then a dot. If you don't put a dot, what happens? Nothing. It works also.
After fix space
Or nothing.
or nothing. Okay.
No, pero el dot no va a pegar. Okay, so now we have the Hausmann test. The Hausmann test is interesting because it gives you a lot of information, and the reason why you don't have directly a number, because typically in tests you're looking for a number, but here it gives you a lot more than a number because it wants to give you a lot of information about the actual differences between the estimates. So for instance, this estimation of experience is about the same in fixed and in the generalized squares. Is the same, about the same or not? This about the same or not?
No.
Yes? No? The difference is how much? 4%? How, when we come to here, the next one, union, is about the same or not?
No.
No. How much more? 25.
30.
25% more. Married is about the same? No, it's like 30% more. South, the same or not?
No.
No, it's changed switch sign, and the difference is very large. Very large. It's 100% or more. And then ours is about the same or not?
Yes.
Yes. So if you look at the difference is here, and it's telling you how much it is, the difference. It would be nice to compare that difference with something that will be like the standard deviation of the difference. No? Standard deviation. It would be nice if we could do that, because that helps a lot. No? In reality, we cannot do exactly that, but we do something similar, which is the square root of the diagonal of the difference of the matrices. So the square root of the diagonal, the whole idea is similar to the standard deviation of that difference. It's very similar. It's not exactly the same, very similar. So here, what you would like to do is compare the difference with the standard deviation, Although, and what would you do if you compare the difference with the standard deviation? What is the test? F test, T test, chi-square? T test would be the T test. Why don't we have a column of T test? State I forgot? Why? Because it is not quite right. So that is why it doesn't put a column there. Yeah? So you can think of if you divide this into this is like more than 5, so that would be significant. If you divide this into this, it would be more than 3 times significant. If you divide this into this, it would be more than twice significant. So all these differences turn out to be significant. So it's not that you look at them and say big or small. You think of this as a t-test that is going to help, although it is not totally precise. You know why it says SE, standard error? Not by coincidence. because this is close, very close.
So we can interpret the difference with the standard deviation like significance or something.
Yeah, you have to divide the difference into the standard deviation,
Okay.
which is not exactly the standard deviation, but approximation.
Okay.
Yeah, and that is why we don't have a t-test. But the idea is that you can decide which ones of these coefficients are really failing and which ones are more or less the same. In this particular case, all of them are failing. But this is not always the case. Sometimes it fails, sometimes it not. So we have here like individual tests. We could have a set of individual tests. However, we would also like to have a joint test of significance of the differences, and the idea is that we have that test here, 41.05. 41.05 is the computed test. 41 is big or small? It's big. And then if it is big, what do? We reject the null, or we do not reject the null?
We reject.
Reject. If we reject, can we use GLS or no?
We have to use fixed effect.
Yeah, we would have to stay with the covariance or OLS estimator. So we could not use generalized least squares. So we have to remember that this is always one way of deciding between two different estimation techniques and one model. One model is a random effect model. Two estimation techniques are OLS and GLS. I know that it sounds weird, but it is like that, exactly like that. Right? So we are deciding between two different estimation techniques. Do you have any questions on this Hausmann test? This is quite simple and it's useful. Sometimes one makes a big mistake, and the big mistake is to try and do the Hausmann test comparing the GLS with the OLS. So I would like Angel to do this, to do the mistake and do it the other way around. So what we would have to do is to estimate first using the random effects, store those estimates, and then estimate using the OLS. So and then ask for a Hausmann test, and you will see that we do have problems. So the test is not the same depending on which thing you test first.
Can I ask a question?
Yeah.
It is not very technical, but for example, if we are analyzing countries that are like entities that cannot be understood as causal extractions, so like, but the Hausmann test tells us that we have to use a random effect. In this case, it would be correct.
No, again, no. If we have a model which is a random effects model, and we want to decide how to estimate by OLS or GLS, then Hausmann test is helping.
Okay, and if the Hausmann test say, okay, use a random effect, for example,
No.
use
No,
GLS.
use GLS.
GLS. But I'm analyzing country.
Yeah.
Would it be correct to continue with fixed effect despite
Yes,
the Hausmann
because
test?
the Hausmann test has very nice properties, but one of the not very nice properties that it has is very little power. It has very little power. So it may be the case that you have correlation between alphas and x's, but you do have correlation, important correlation, and the test fails to detect. This is common. So in this case, it is entirely possible that you want to use the covariance estimator or OLS estimator, even if your test does not reject.
Thank you.
I have one question. I want to ask you, for example, the null hypothesis here, the OLS is appropriate and GLS not appropriate? Or
No, the null hypothesis is that there is no correlation between individual effects alphas and explanatory variables x's. That is the null hypothesis. The alternative hypothesis is that there is correlation between alphas, individual effects, and explanatory variables x's. So this is the null and the alternative. So now you did RE, and then what you want to do is estimates store RE instead of fix. And then you want to estimate using comma FE. Comma FE would be estimation by OLS. And then if you put Hausmann RE, so if we do that, you see that it is not the same to do it in an order or the opposite order. It is very different. You see that the number we get is negative, and you know that a distribution of chi-square cannot be negative. Okay? So it is impossible. So it says here that the model fails to meet the asymptotic assumptions of the Hausmann test. So it gives you a lot of problems. No, but the problem is that we have done it in the reverse order. So when this happens, and this happens very often, you just remember that we have to do it the other way around. It is not difficult. It's just to remember that the order is important. Do you have any questions on this? Okay, so now let's move to the next the next step, and the next step is to work with a dynamic model. Dynamic model is the topic of lesson number 4. So now we are going to use a dynamic model. The dynamic model, all we need to do is create a variable which is the lag dependent variable. The lag dependent variable is has to be generated using the stata commands, and the command for this is generate L weight 1 equals L weight so this is the command. The command, of course, you can look it up in the help. It is not very easy to find in the help. I was looking for it in my office, and it's not so easy to find the command. The command is you have to put a square brackets and a lower, what do you call this? Lower, lower underscore, and then n minus 1, and then close the square bracket. So that is the way to generate a variable which is the lag dependent variable. So now it tells you that you have one missing value. One missing value. So, are you sure that this is correct or not?
Yes, correct.
No, it's terribly wrong. No, terribly wrong. Why? Because we have how many people? Like 800 or something. And if we generate a lag-dependent variable, that would mean that we lose like 800 observations, not one. So if we do this, we are assuming that the last observation of a guy was the first of the previous person.
Okay.
Terrible mistake. Huh? So what we have to do whenever we estimate this model, and it is a dynamic model, we have to cut the sample. We have to get rid of the first year. We have to get rid of the first year. So we are going to have to use a sample if. Remember that all of you have accessible all these commands in the documentation. So if you want, you can have it open in half a screen so that you can see what we want to do, so that I don't have to do everything here. So what we want to do here is to write the equation. So let's write the equation as it was before. Let's start with the simple equation, just the fixed effect. And then fixed effect is comma Fe, and then we want to use the lag dependent variable. This one, L weight 1, we want to use it as the first explanatory variable. So we want to write xt reg L weight and then L weight 1. Okay, so that would be the equation that we want to estimate. But we cannot use the first year. So how do we do? I remember you have it in the documentation. So anyone can look at the documentation and see what we have to do. You remember that the first year is 1980. So we want to estimate leaving out 1980. We can do it in many different ways. Typically, you put an if condition. If year equal or bigger, equal or
different.
It's equal or bigger. Together. And then 1980, I guess. So this should work for something similar, the other way around.
I think it has to be before the comma.
Eh? So let's see. Well, you should know because all of you have this in the documentation. So you should be able to tell me, help me, instead of I telling you. Yeah?
90,
Eh?
81, 52, 1.
$19.80. Huh? because if it is
Equal or
equal or bigger. But you have it there. I'm not going to tell you. You have it there. Check it. Check it. Look at it. You tell me. You tell me.
equal or bigger, 98 is gonna be included. Or not?
Only bigger. ¿Eh?
Bigger, just bigger.
Pero dice él que hay que poner el if before
Yes.
the comma. So let's try. Let's see. What happened?
90, 80.
It has to be, it's, the bigger has to be before the slower.
Good, good. The bigger, bigger or bigger?
Bigger?
Yeah. But mayor or igual.
Hmm?
To me is the equal, I think.
Okay,
You
yes.
don't want, so you're,
1980.
So now
oh yeah, no, that's right, because it's like.
it is working. Sometimes there are different ways of writing the same thing, and that is due to the fact that a lot of commands are old commands, and they are simplified in newer version. So now we have a model which is a dynamic model. The lag dependent variable is here. The lag dependent variable is here, and then what we have here is the same model as before. The same model as before. Eh? But do you remember what happens if one estimates a dynamic model using OLS? What happens? Is it good? Fine? No problem? Big problem? Eh? Big problem. Big problem. So that means inconsistency of the lag dependent variable coefficient and bias in the rest of the coefficients. So very bad, very bad. So we are not going to go very far using OLS with a dynamic model. Not very far at all. You should not do it. Not even try. It doesn't make sense. Because anything that you get is nonsense. So it doesn't matter what you get. Now, what we can do is we can try to do something else, which is estimate by generalized least squares. So we can estimate the same model, the same dynamic model with the same data set, and we can estimate using generalized least squares. You remember that I told you that if you estimate this L wage using OLS, the estimations that you get are biased, downward, inconsistent, and low, no? 0.06 is low, eh? Because it goes between minus and plus 1. So this is not useful, not useful. So let's see what happens if we estimate the same model but using random effects. Random effects. If we estimate using random effects, what happens? What did I tell you that would happen? Would be a good idea? Bad idea? What was the problem with this coefficient? Would be biased upwards or downwards? Upwards or downwards? The previous case it was biased down, and in this case up. What do we learn from this? The only thing that we learn is we don't do it anymore. Because we don't learn anything. So I see that coefficient 0.55 is the same to me as 0.3, 0.9. Doesn't tell me anything. I don't know what to make out of this. So this is not very useful. Not very useful. So I told you that these are not useful. So what is useful in this context? Instrumental variables. Well, instrumental variables turns out to be useful in almost all contexts, no? But also here. So let's see if we can estimate using instrumental variables. One way of doing it, we are going first to go to the Arellano-Bond estimation, which is useful and it solves a lot of problems, but it does not solve all the problems, only some of the problems. But I do want to cover the Arellano-Bond first, just in case. Let's go first to that. How do we do Arellano-Bond? You go to statistics and then go to longitudinal panel data and then dynamic model maybe. And maybe Arellano-Bond. In here, what you do is, this is a very important chart, so I would like you to look at this because there are a lot of things that were not present in the other box, a lot of things. Let's look at one by one. The dependent variable is the same, L wage. Now, the independent variables are the same as before. We are not going to include L wage 1 because that is the dependent variable lag 1. And Arellano-Bond knows how to do this. What happens if you include the lag dependent variable? Nothing. It ignores. No problem. And here we have some options that are exogenous variables previously difference, variables, additional instrumental variables, all these. Then the number of lags of the dependent variable, many things. For the moment, let's leave it like this. Let's don't touch more. Only make the simplest possible choice, and let's see how that simple choice works. The first thing that you notice is that some of the variables have been omitted, but those are the same as in the within estimator. So this is similar in that sense to within. That is no surprise. The second thing is that this the way this is estimated is in difference. So this is not in levels as in the previous cases. It is in difference. So it is the difference of the lag dependent of the dependent variable, and that is why this turns out to be like that. Why observations by group 6? Why 6? We had 8 to start with. Why 6 now? Where did we lose 2 observations?
In the process of this differentiation.
Eh?
In the differentiation.
Yeah, but the differentiation is only one.
One
Where
from
did we-
first and one from the last. If the difference is
Yeah, but it has to be related with differentiation. But I only see one. No?
Because of the lack and the differentiation.
Because the lag and the differentiation. Huh? So there's like two differences. So that's why we only have 6 observations per individual. And then what you have here is the lag dependent variable. How much is it? The coefficient is 0.14. No? 0.14. Is it the same as before? Similar to the 0.05 or similar to the 0.5? No, it's different. No? It's different. So this estimation is different from the previous one. And you see here the omitted variables. You see here the estimate for the coefficient of experience, education, union, married, south, hours. You have to notice that these estimates may be similar or not to the previous ones. So if you look at them, I remember them, some of them are very close. Some of them are very close, like the married, union is not so close. Education was about 0.10 before. So some of them are close and some of them are not close. No? That means that this is a different specification. Now we have a dynamic model. The dynamics absorb some of the significance of the variables, but in any case, there are a lot of highly significant variables. Some of them are insignificant, like this, but some of them are significant. So the estimation is different. This is a dynamic model estimated in differences. So it is not the same, and that is why the estimates don't have to be exactly the same. It is quite a different model, a dynamic or a static model. This model has been estimated using lags of the dependent variables. Let's look at here it says that we are using the second lag of the wage, of the log of wage. We're using the second lag to as a instrumental variable, and this says that standard variables are D. What is D? What is D? Difference. So we're not using expert, we're not using union. It's difference. It's difference. Yeah? It's not the same. And this would be the output for this dynamic model. Sometimes you are happy with this or not, but the problem is that if you use incremental variables, the estimates are not unique. So there are a lot of things that you can work on this output. This is not like the end of the story. This is the beginning of the story. The beginning of the story, because now you have to do trials, you have to work, maybe choose another instrumental variable. So let's do something like this. Let's go to you see the number of instruments here up here is 27. 27 is a little or a lot? Little, lot? The problem is, you see, depends on the number of of the coefficients that you want to estimate. If you want to estimate here like 5 or 6, then 27 is a lot more than 6. And there are like 19 over identifying restrictions that you may be happy or not with them. May be happy or not. So it is possible that we have a situation in which we are not happy. We're not happy because using too many instruments may cause bias, and it may cause also problems of collision between instruments. So the Sargan test may apply, may be needed to decide if the identifying restrictions are too many. So what I would like you to do from this beginning is to go and go back to the box, to the estimation box, and see if we want to change things. Because typically one does not want to use a lot of incremental variables, but only a few. For instance, you can put here a maximum number of dependent variables that you want to use, or maximum number of explanatory variables that you want to use. So let's touch this and change the default. The default is what you see here when there's nothing to check. The default here is 1. The default here is 1. So we may want to even go further and go to 2. So let's see what happens if we change the default. If we change the default, of course the maximum number is the same. The number of instruments is 17, and you see that the differences in the estimates are not very big. Not very big. Please notice that these three are insignificant. So typically one does not want to interpret insignificant coefficients, because it is like trying to explain why something is important when it is not important. It doesn't make sense. So this would be a different estimation technique, also instrumental variables, and what we can do is we can check and see if we like those differences or not. I would like you to call your attention to the Wald chi-square 7. What does that mean? Wald chi-square 7 up here.
It's a test of that says that we are over identification or not, right? Something like that.
No, because this is a test which is related to the estimated coefficients. Not the incremental variables. So what is this? Wald chi-square 7.
The number of coefficients that are not omitted.
That are?
All the variables that you can the values that you saw and are not omitted.
No, but you see, this is a test about the estimated coefficients. No? But what is it telling you about the estimated coefficient?
maybe is it a kind of F-test for jointly significance of the 7?
Yeah, it is the same idea as the F-test. No? It is a test of joint significance of all the estimated coefficients. All the estimated, no, those are that are not estimated. We don't care. No? So it is a test of significance of all the estimated coefficients. So what is it good? That it is big or small? Big. No? Right. If we want the model to be significant, if we don't want that, that's a different story. No? But and 115,000, is it big or small? Eh? Big. And how do you know? Because do you know because of this? P-value? P-value is 0. No? P-value is 0. So in this case, the null hypothesis is that each individual coefficient is equal to 0. Each one. All of them. Right? And the alternative is that one or some or all of them are different from 0. So in this case, what is it telling us, the test? That the coefficients are jointly significant or insignificant? Significant. Significant. So we like a big value of the coefficient of this test. Do you have any questions? So let's go back to the box. The box is very important because the box allows you to control, to use more coefficients, less coefficients. You can use robust estimations. You can use many different. So please look at things that you may want to do with those within those boxes, and then we'll do something different. For instance, I can see that you may want to use robust standard errors, no? And one of the choices is GMM robust. You know, it may be a good idea because if we came all the way to here and not use robust standard errors, it's a waste of time. And what else can we do? Something that is useful. Here you can use more flexibility than in the previous estimation techniques. You can use a lot more flexibility because this box is synthesizing everything that we could do in the DPD all time, but now it can be done in this box. So a lot of things, a lot of options that you may want to use or not. Remember, typically, that if we want to use a small number of lags, you don't want to use 300 lags. Why? You remember why we don't want to use long lags of the variables? Because the estimates are sensitive to outliers. No? And we don't want that to happen. We would rather have this different. We would rather have short lags. So let's now do the same thing, but using the robust GMM standard errors. Robust means that they are asymptotically correct, that they have been, the estimation has been corrected, the estimation of the standard errors, not of the coefficients, only the standard errors. The coefficients are good enough, so that's why we don't correct. this is 13,000. You remember how much it was before? Like 115,000. So it has changed. You see, the estimation, the point estimations have changed or not, from the previous one. You can go up and down your screen.
No, the coefficients are the same. Right?
Are the same. Okay, only the standard errors have
Yeah.
changed. And the T statistic, I mean, what is this Z? I don't remember. What is this Z statistic? Remember? Did I tell you before or not? No? Well, the here and in many other situations, we don't know exactly the distribution of the estimators, and therefore we cannot write a T, which is a ratio between the estimation and the standard deviation. We cannot know that because all the estimations are approximation. So in that case, instead of writing here the T, we write the Z. Z is the approximation to the T, and it's an approximation based on the standard norm. It is, if you want to think of this as being exactly the same as the T, that's okay. It is almost exactly the same. But this is a standard normal asymptotical. So, if you want to know how much is this 4.32, this is the ratio between the coefficient and the robust standard error. Ratio between the coefficient and the robust standard error. So this is the column called Z. Z. The next column is the p-value of the Z. So this is telling you if this particular variable has a coefficient which is significantly different from 0. So this is the way in which it works. It is exactly the same as the T, exactly the same, no difference. The only difference is mainly the name, which is Z instead of T, and the 95% confidence interval of the coefficient is the same as before. So the center of the interval is the estimated coefficient, and it opens upwards and downwards to a standard deviation. So this is the 95% confidence interval, the same as before, exactly the same. Do you have any questions? Now, this idea of Arellano bond, it is like a little black box because it chooses the number of lags and chooses a lot of things. It allows you to do some things, but not everything. So let's go and save all of this. So save this output, and let's estimate this using instrumental variables in levels. It is not going to be the same because it is in levels. So let's now go back to the normal estimation, and we are going to use instrumental variables to estimate the model. Instrumental variables, I told you that it is important and it's something that you have to learn. And you not necessarily want to do everything automatically like here. You may want to use your own instrument. So let's go and find where we have the box for instrumental variables. No? Because we could do this by hand, but it takes more time. It's better to go to the box for instrumental variables. No, not this one. The linear model. Vamos a ver aquí arriba. The command for instrumental variables in Stata is the one that you have. You have already the commands in the documentation. It is xt id reg. So this is the command that you want to use. You have it in the documentation. So please help me to see how it works. The first thing that is that you need here to put the L weight. And then you may want to use also the dynamics. We see that we are still in the dynamic model, right? The dynamic model. So we will have here L weight 1, and then the some variables, all the explanatory variables. I want all the explanatory variables here. In the list, all the explanatory variables. So you have again this, and then it will be the estimation technique. We have just seen that what happens if we estimate like this. What happens? If we estimate the model as it is, what happens? Random effects, dynamic. Disaster. Huh? Everything is going to turn disaster. Huh? Okay, so we have to use instrumental variables, and the instrumental variables that we are going to use, you can put them here. So if you have the documentation, just help Angel because I don't have the documentation. Well, Angel has the documentation also. So what I would like you to do now is to write what would be the general setup of the equation. The equation, we will write it like xtid reg, then the dependent variable L weight, then all the independent variables that we were using, like 6 or 7 that we were using, and then we are going to use a new part of a command that is this parenthesis. And this parenthesis is going to be telling theta that you're going to instrument one variable. In this case, it's going to be the lag dependent variable. And we are going to instrument it, for instance, using lags of the independent variables. Those lags of the independent variables, you have to create them. You have to create them one by one. It takes like 2 minutes at the most to create all the lags of the dependent variable, of the independent variable. So that would mean if you want to create the variable expert, it would be lag of the expert so this would be like this. And you have to do the same for all of the explanatory variables, so that you can create your own set of instruments.
With the dummy variables also?
No.
No.
Which dummy?
Hispanic, for example?
No,
It's
but
not no lag, no?
no. You don't want to lag those.
Right.
So only the continuous.
Not lag. No, this is not lag.
Yeah, and especially because you know
Yes.
that those variables don't change a long time. If they change a long time,
Without the
even if
second
they're
L.
dummies, you
Sí,
have to
ahí.
do.
The
Yeah.
expert.
If they change, not the case.
Thank you.
So now, if we want to think, why are we using the lags of the explanatory variable? Why? Why are they instruments? Maybe they are not. No?
Because there is a correlation on the past.
Yeah, there is a correlation between the lag dependent variable and the lag independent variable. No? And is there a correlation between the lag independent variables and the error?
Could be.
But in principle, the error does not have a relationship with the previous, with the past, with all the past. No?
should we generate the all variable similar to the dummy variable hours, south, like this, or not?
Yeah, you have to generate all of them. But I don't know if I was telling her that if there is a variable that does not change a long time, you don't have to generate it because it's the same. But those variables we cannot estimate their effect. Aquí. So you have to use L weight 1 if this is the name that you have been using, equal, and then the names of the lags of the independent variables that you have created. So you write like the almost complete equation, and then anything that is endogenous, you just instrument it using the lags, in this case, of the independent variables. So this is quite simple because, in principle, this could be very long and very hard to do, but in Stata it is extremely simple.
So the instrument variables are between parentheses, right?
Well, there is a parenthesis, a big parenthesis, and at the beginning of the parenthesis we have the variable that is endogenous. In this case, the lag value of the dependent variable. Then you put an equal sign, and then the names of the independent variables that have been lagged to become instruments. Do you have any questions? So let's see what happens. What happened?
These random effects.
Is this random effects or disaster effect? I see disaster. What kind of disaster? I see disaster. What is the problem? The big problem. Big. Big problem, no? Because you said that if we take difference, what happens?
We are going to meet what?
1 times 500.
1 times each individual.
So what happens? We forgot what?
to put the if.
The if, no, the if. Important the if or not important?
Yeah, it's very
Very important because otherwise we are doing something that we don't even have a clue of what we are doing. So So now this is something different. You see, 3 variables dropped, and what happens in the previous case? Also 3 variables dropped. So, but the coefficients, are they the same? Minus 0.36. The same? No, quite different. Eh? Quite different. So you see that if you estimate using instrumental variables, you do have non-uniqueness very apparent. No? You see a lot of situations in which the estimates are very different from one case to the other. So I think that what I would like you to do now is think again about your assignments, your project assignments, because I think that most of you did weird things, like everybody wanted to use Big 9 salary DTA. Why? I said 1 or 2 names, only one. And then a lot of people didn't sign up for any database. So why don't you take a few minutes to fill this out? Think about this, decide what you want to work on, and start working on it. We still have 15 days. Maybe if you need one more week, that's fine. But I would like you to work on this and think about this slowly. I think that what we have been doing today is more or less what you need to do for your assignment. And of course, we still have another class next week in which I will talk again about incremental variable and simultaneous equations. But it is relatively similar to the dynamic case. So we're going to go again through a practice next week. So please take your time to write slowly what you want to write. If you want to use a specific database, because it is important, I see everybody wants to do Big 9 salary. Why? I've never seen that particular database used by anyone. So I don't know, maybe you have more information.
Excuse me, can we do the same project or no?
Eh?
This project? Wait.
No. WagePan, no. You can use anyone but WagePan because this is already done. Huh? You need to do something new, something that you haven't done before.
Excuse me, I could not attend the last lecture. Where do we take the databases?
Everything is in the web page.
Oh, okay.
Everything is the web page, so you can look it up now, and then make a decision. Fast and furious decision.
Excuse me, the background theory is in the Woolridge book or no? The theory?
Yeah, the theory of each of the databases is in the Woolridge book. It's in the Woolridge Introductory Econometrics book and also in the cross-section and panel data book.
The book is available in this library?
Yeah, or you can look it up. Yeah.
In the Hausman test, said that we should
use OLS
You go there.
models.
Oh, we can check it.
The classes, they cannot follow.
It's all loaded.
But
You have to
some
follow
variables
this path.
are no
have to follow this path.
Some variables
That
are
panel data,
in that.
DVDD,
So,
and then panel data. You start, look, you start here on panel data, and then you have to go to data, and then to panel data. And you have,
there are a case
you have all the data.
16 order.
It's 16, I can check.
are in different.
Yeah, sometimes they are more or less indifferent. When you have
That's it.
an estimation
Panel data,
of
that,
the Hausmann
that's
test
all.
that
all
is
the data
borderline
sets that are
maybe
on.
12 or 15, so it's
Thank you.
not too big.
I have another question. When we decide to choose between static
So we can use
In
it.
principle, you would have to think that economics is
so it is so
Te la
it is
pongo en-
the majority of the time is better to use
Yeah.
dynamic
Mayor,
in principle, yes, if you can do it.
sí, pero sí.
Yeah, I was answering a question, and it is a very important question. Is what is it better to use static or dynamic model? In general, it makes sense in economics to think about dynamic model, because typically you have a lag in the implementation of decisions, or it takes time for investment, it takes time for adjustment. So it's usually dynamics who play an important role. No? So if you take a decision today, usually you stick to the, say if you buy a car today, so you don't buy a car next week or next year. You keep buying new cars, so you keep the car for quite some time. So you have quite a sticky decision. That is typically modeled by dynamics. So this is one important thing, and the other one is that in the next class I will convince you that in economics in general, one equation models are not very sensible. You use several equation models, and simultaneity is normal, and it's common since the first few classes in economics that you got when you were kids. So today I wanted to convince you that dynamics is important, and the next class I will convince you that it is the simultaneity which is important, and simultaneity is the common situation, not the independence or the isolation, the one equation world. It is typically the multiple equation world which we're typically dealing with, and we will deal with that next week, next Wednesday.
So you have to choose one of the databases that are in there, and then to do some
Yeah, but then
estimate things with it.
yeah, Angel was choosing databases that were panel databases, and they are in the document. And so you have to look at one of these and work with one of these.
And with
What you need to do is to follow the instructions that you have in the web page, and that I was commenting in the previous class, and make sure that you do something that is makes sense in all respects, and follow the instructions, because the instructions are designed to help you.
No.